Hey everyone, welcome back to another strange journey through the most bizarre corners of human history. Tonight we're diving into something that'll probably make you question whether your own weird dreams might be hiding the next Nobel Prize. We're exploring the scientists who literally dreamed their way to world-changing discoveries. So before you settle in for the night, hit that like button and subscribe, but only if you actually find these stories as mind-bending as I do. And drop a comment letting me know where you're watching from tonight and what time it is. I always love seeing our global community of insomniacs and dream enthusiasts checking in from every corner of the planet. Now, get comfortable, dim those lights, and prepare to discover how some of humanity's greatest scientific breakthroughs came not from years of careful calculation, but from the bizarre theater of sleeping minds. And hey, if you end up drifting off somewhere in the middle, that's exactly what we're going for here. You know, I've always found it fascinating that we spend a third of our lives unconscious, yet somehow that's when our brains decide to solve problems that stumped us while awake. It's like your subconscious is this brilliant scientist who only shows up to work after you've fallen asleep. Dreams don't just entertain us, sometimes they literally reshape reality. Anyway, let's start with what might be the most famous case of a dream-changing chemistry forever. So picture this, it's 1865 in Belgium and August Kekulé. This German chemist with an absolutely magnificent beard that probably took longer to maintain than most of his experiments is sitting by his fireplace completely stumped by one of chemistry's most annoying puzzles. Now, before we dive into Kekulé's world-changing dream, let me paint you a picture of what chemistry was like in the 1860s. This was the Wild West of science, folks. There were no fancy computer models, no sophisticated instruments that could peer into the molecular world. Chemists were essentially playing with invisible building blocks, trying to figure out how atoms arrange themselves based on nothing more than chemical reactions and educated guesswork. Kekulé himself was quite the character. Born Friedrich August Kekulé von Stradonitz, because apparently German names weren't complicated enough without throwing in some nobility, he originally wanted to be an architect. And honestly, that architectural background probably helped him think about molecular structures in three-dimensional terms. Who knew that learning to design buildings would be perfect training for designing molecules? But here's where it gets interesting. Kekulé wasn't just any chemist. He was obsessed with what he called constitutional formulas, which was basically his way of trying to map out how atoms connected to each other. This was revolutionary thinking at the time. Most chemists were content to know that a compound contained, say, 6 carbons and 6 hydrogens without worrying too much about how they were arranged. Kekulé, however, was convinced that the arrangement mattered. He believed that if you could figure out the structure of a molecule, you could predict its properties and behavior. This might seem obvious now, but in 1865 it was cutting edge theoretical chemistry that most of his colleagues thought was unnecessarily complicated. For years, scientists had been trying to figure out the structure of benzene, C6H6. They knew what elements were in it. They knew its molecular weight, and they knew it had some very strange properties. Benzene was incredibly stable, much more so than other compounds with similar formulas. It didn't behave like other hydrocarbons. It was almost like this molecule had its own special rules. Every model they tried either didn't work chemically or just looked ridiculous on paper. Linear chains made no sense. The chemical properties were all wrong. Branch structures were equally problematic. 3. Dimensional configurations that looked like molecular furniture from IKEA. And trust me, they were about as useful as IKEA instructions written in Swedish. Kekulé had been losing sleep over this problem for months. I mean, this guy was literally obsessing over carbon atoms, which honestly sounds like the most German thing ever. He tried every possible arrangement he could think of. He'd filled notebook after notebook with molecular diagrams that looked like abstract art gone wrong. Picture this man in his study, surrounded by papers covered in chemical formulas. A oil lamp flickering as he scratched his beard and stared at the same 6 carbon atoms for the 1000th time. His colleagues probably thought he was going insane, spending months on a single molecular structure when there were so many other chemical mysteries to solve. But Kekulé couldn't let it go. He knew that benzene was important. It was found in coal tar, it was used in dyes, and it had this mysterious stability that suggested something fundamental about its structure. If he could crack this puzzle, it might unlock secrets about how atoms actually behaved. The winter of 1865 was particularly brutal in Belgium. Kekulé would often work late into the night, his study heated only by a small fireplace that cast dancing shadows on the walls. He'd pull his chair closer to the fire, spreading his chemical notes across his lap, trying to will the solution into existence through sheer determination. On this particular winter evening, after staring at his notes until his eyes burned like he'd been peeling onions in a chemistry lab, Kekulé finally dozed off in his chair, and that's when his subconscious decided to give him the most important chemistry lesson in history. In his dream, Kekulé saw atoms dancing. Not metaphorically dancing, literally waltzing around like tiny molecular ballerinas wearing tutus made of electron clouds. Carbon and hydrogen atoms were spinning and twirling, forming long chains that snaked through his dream like some kind of atomic conga line, set to music only molecules could hear. Now, this might sound charming and whimsical, but imagine dreaming about dancing atoms when you're trying to solve serious scientific problems. It's like your brain is mocking you by turning chemistry into a Disney movie. I can picture Kekulé's sleeping mind thinking, "Oh, you want to understand molecular structure? Here, let me show you atoms doing the waltz. You're welcome." The dream was incredibly vivid. Kekulé could see individual atoms with perfect clarity, carbon atoms as dark spheres, hydrogen atoms as smaller, lighter spheres, all connected by what looked like golden threads that pulsed with their own inner light. The atoms moved with purpose, forming chains that grew longer and longer, creating molecular conga lines that stretched across the landscape of his dream. But here's where it gets really interesting. In the dream, these dancing atomic chains weren't just random. They were forming patterns, creating structures that seemed to follow their own internal logic. Kekulé could see how carbon atoms preferred to connect to other carbon atoms, how hydrogen atoms attached themselves to available bonding sites, how the whole system balanced itself with mathematical precision. For what felt like hours in dream time, Kekulé watched this atomic ballet. The molecules were performing for him, showing him their secret choreography. He could see how different arrangements created different properties, how the shape of a molecule determined its behavior, how structure and function were intimately connected. Then something amazing happened. In the dream, one of these dancing atomic chains suddenly grabbed its own tail and formed a perfect ring, like a molecular Ouroboros eating itself, except instead of ancient symbolism representing eternal cycles, it was the key to understanding one of chemistry's greatest mysteries. The moment was absolutely electric, if you'll pardon the pun. Kekulé could see that this ring structure wasn't just possible, it was inevitable. The 6 carbon atoms formed a perfect hexagon, each one bonded to 2 others, with hydrogen atoms attached like little molecular decorations. The structure was elegant, symmetrical, and explained everything about benzene's unique properties. But the dream didn't stop there. Kekulé's subconscious, apparently not content with just solving the benzene puzzle, showed him how this ring structure could be modified. He saw other atoms attaching to the ring, creating derivatives with different properties. He saw how the ring could be part of larger molecular structures, how it could serve as a building block for more complex compounds. When Kekulé woke up with a start, his fire had burned down to embers and his neck was stiff from sleeping in the chair. But he immediately knew he'd found his answer. The solution wasn't a chain or a branch, benzene was a ring. 6 carbon atoms arranged in a perfect hexagon, with hydrogen atoms attached like little molecular Christmas ornaments. He grabbed his pen and started sketching furiously, trying to capture what he'd seen in his dream before the details faded. The ring structure made perfect sense of benzene's properties. It explained why the molecule was so stable, the ring distributed chemical forces evenly, creating a structure that was remarkably resistant to chemical attack. But here's what I find absolutely hilarious about this story. Kekulé spent years using logic, mathematics, and rigorous scientific method to solve this problem. He approached it like the rational German scientist he was, methodically testing every possible arrangement. And in the end, the answer came from a dream that sounds like it was directed by Walt Disney on a particularly creative day. The benzene ring structure that Kekulé dreamed about became the foundation for understanding aromatic compounds, which led to the development of dyes, pharmaceuticals, plastics, and basically half of modern chemistry. Every aspirin you've ever taken, every synthetic dye in your clothing, every plastic polymer in your phone, they all trace their origins back to a German chemist's dream about dancing atoms. Think about that for a moment. One guy's weird dream about molecular ballet became fundamental knowledge that shapes how we understand reality. The benzene ring is now taught to every chemistry student in the world. It's literally drawn on blackboards millions of times every year. Kekulé's dream became one of the most reproduced scientific diagrams in history. And you know what's even crazier? Kekulé later said that his most important scientific insights always came from dreams or daydreams. This guy basically built his career on paying attention to what his sleeping brain was trying to tell him. He turned dream analysis into a legitimate research method, though he probably didn't put it quite that way in his scientific papers. The benzene ring discovery opened up entire fields of chemistry. It led to the development of organic chemistry as we know it today. It explained how aromatic compounds worked, why certain molecules had unusual stability, and how to design new compounds with specific properties. But perhaps most importantly, Kekulé's dream showed that scientific breakthrough sometimes requires thinking in ways that conscious logic can't achieve. His rational mind had been stuck in linear thinking, atoms arranged in chains or branches. It took the non-linear logic of dreams to reveal that sometimes the best solution is circular. Makes you wonder what other breakthroughs might be hiding in our own weird dreams about talking animals, flying through grocery stores, or whatever bizarre scenarios our unconscious minds cook up while we sleep. Maybe the next great scientific discovery is just a good night's sleep away, waiting for someone brave enough to take their dreams seriously. Speaking of scientists whose dreams changed the world, let's talk about Nikola Tesla, a man who was essentially a human lightning rod with a mustache that could conduct electricity on its own. This is the story of how alternating current, the electrical system that powers your entire modern life, came to Tesla through a series of dreams so vivid and detailed that they seemed more like electrical engineering, courses taught by the universe itself. But before we dive into Tesla's revolutionary dreams, let me paint you a picture of what electricity was like in the 1880s. This was the dawn of the electrical age, when the very concept of harnessing lightning was still mind-blowing to most people. Electric lights were a novelty that made people gasp in wonder. The idea that you could flip a switch and illuminate a room seemed like pure magic to a world that had been using candles and gas lamps for centuries. Tesla himself was quite the character, and by character, I mean he was probably the most brilliantly eccentric human being who ever lived. This was a guy who was obsessed with the number 3, refused to shake hands because of germs, claimed he could communicate with pigeons, and had a photographic memory so precise that he could conduct entire engineering experiments in his mind without ever building a prototype. Born in what is now Croatia during a lightning storm, which is either perfect foreshadowing or the universe's idea of a really heavy-handed metaphor, Tesla showed signs of electrical sensitivity from an early age. He would see flashes of light when touching certain objects, could sense electrical fields, and claimed that his fingertips would sometimes glow in the dark. By 1882, Tesla was working for Thomas Edison in Paris, trying to improve the direct current electrical systems that Edison was promoting. Now, here's where it gets interesting. Edison was convinced that direct current was the future of electricity. DC power was simple, straightforward, and safe. But it had one massive problem. It couldn't travel long distances efficiently. With DC power, you needed a power station every few miles because the electrical energy would dissipate over distance. This meant that Edison's electrical future would require thousands of power plants, massive amounts of copper wire, and an incredibly complex distribution system. It was like trying to water a city by placing a well in every backyard. Tesla, however, was convinced that alternating current was the answer. AC power could be stepped up to high voltages for long-distance transmission, then stepped down to safe voltages for home use. It was elegant, efficient, and could power entire cities from a single generating station. But there was a problem. Nobody had figured out how to build an efficient AC motor. The existing AC motors of the time were absolutely terrible. They were inefficient, unreliable, and had a tendency to catch fire at inconvenient moments. The motors relied on brushes and commutators, physical contacts that would wear out, create sparks, and generally make the whole system unreliable. It was like trying to build a car where the engine had to be rebuilt every few miles. Tesla had been puzzling over this problem for months. He knew that AC power was theoretically superior, but without a practical motor, it would never replace Edison's DC system. He needed to find a way to create a rotating magnetic field without using mechanical contacts. Essentially, he needed to make electricity itself do the rotating. For weeks before his breakthrough, Tesla had been having the most extraordinarily vivid dreams about wheels made of pure electricity. Not metaphorical wheels, actual spinning disks of electrical energy that rotated in perfect circles, creating their own magnetic fields as they spun. In these dreams, he could see the electrical forces flowing in curves and spirals, creating patterns that pulsed with their own rhythm. The dreams were so realistic that Tesla claimed he could actually feel the electromagnetic forces, like standing too close to a massive generator. The spinning wheels in his dreams would emit this deep, thrumming sound that seemed to vibrate through his entire body. He would wake up with his hands tingling, as if he'd been conducting electricity while he slept. But these weren't just abstract visions. Tesla's dreams were incredibly detailed and technically precise. He could see exactly how the electrical currents would flow, how the magnetic fields would interact, how the forces would combine to create rotation. It was like his sleeping brain was running complex electromagnetic simulations. Tesla described these dreams as being more vivid than his waking life. The electrical forces in his dreams had colors, blues and purples and golds that shimmered and pulsed with the rhythm of alternating current. The magnetic fields were visible as flowing lines of force that bent and curved through space. The whole electrical system was laid out before him like a cosmic blueprint. But the most important part of Tesla's dreams was the realization that he didn't need mechanical contact to create rotation. In his dreams, he could see how alternating current itself could be made to rotate by using multiple phases of electricity. Instead of one alternating current, he could use 2 or 3 currents that were slightly out of phase with each other, creating a rotating electrical field. Picture this. Instead of having one wave of electricity, you have 3 waves that are offset from each other by 120 degrees. When you combine these 3 waves in a motor, they create a rotating magnetic field that spins smoothly and continuously. It's like having 3 people pushing a merry-go-round, but instead of people, it's electrical waves, and instead of a merry-go-round, it's a magnetic field. The moment of revelation came during that famous walk in Budapest in 1882. Tesla was strolling through the city park with his friend Anthony Szigeti, reciting lines from Goethe's Faust, because apparently he was the kind of guy who memorized German poetry for recreational purposes. The sun was setting, casting long shadows across the park, and Tesla was in one of his philosophical moods. As he recited the lines about the eternal struggle between light and darkness, something clicked in Tesla's mind. All those dream images of spinning wheels of light suddenly coalesced into a complete understanding of how to create a rotating magnetic field. He could see the entire system, the polyphase currents, the rotating field, the smooth operation without mechanical contact. Tesla stopped walking so suddenly that his friend thought he'd had a stroke. Instead of explaining what was happening, Tesla grabbed a stick and started drawing diagrams in the dirt, sketching out the rotating magnetic field principle that had been spinning through his dreams for months. The diagrams he drew that day became the foundation for the modern AC motor. Tesla had solved the problem that had stumped electrical engineers for years: how to create smooth, efficient rotation using alternating current. His dream-inspired insight made it possible to build motors that were more efficient, more reliable, and more powerful than anything that had come before. But here's what's really remarkable about Tesla's breakthrough. He didn't just solve the technical problem of AC motors. His rotating magnetic field principle opened up entirely new possibilities for electrical engineering. The same principle that made AC motors possible also made possible generators, transformers, and the entire electrical grid system that powers our modern world. Tesla's polyphase system, the technical name for his multiple wave approach, allowed electricity to be generated at power plants, stepped up to high voltages for long distance transmission, then stepped down to safe voltages for home use. This made it economically feasible to build large, efficient power plants that could serve entire cities rather than the small, inefficient DC stations that Edison's system required. The war between AC and DC, sometimes called the War of Currents, was essentially won the moment Tesla had his dream-inspired breakthrough. Edison's DC system, no matter how much he promoted it, couldn't compete with the efficiency and practicality of Tesla's A system. Within a few decades, alternating current had become the standard for electrical power worldwide. What I find most fascinating about Tesla's story is how his dreams weren't just metaphorically helpful. They were technically accurate in ways that shouldn't have been possible. Tesla was dreaming about electromagnetic phenomena that weren't fully understood by the scientific community of his time. His sleeping brain was somehow running calculations and simulations that his conscious mind couldn't perform. Tesla later said that he never needed to build prototypes because he could perfect his inventions entirely in his mind, and apparently in his dreams. He would visualize a machine, let it run in his imagination for weeks, then examine it for wear and defects. That level of mental precision is almost superhuman, but it becomes even more extraordinary when you realize that much of this mental work was happening while he was asleep. The AC motor that Tesla envisioned in his dreams became the foundation for the second industrial revolution. Electric motors powered by Tesla's system drove the machinery that built the modern world: factory equipment, transportation systems, household appliances, and countless other applications that we now take for granted. But Tesla's dreams didn't stop with the AC motor. Throughout his career, he claimed that many of his most important inventions came to him through nocturnal visions. His wireless power transmission experiments, his radio technology, his ideas about wireless communication, all of these emerged from what Tesla called his mental laboratory, where he could experiment with electrical phenomena in ways that weren't possible in the physical world. Tesla's approach to invention was almost mystical. He would immerse himself in a problem, studying every aspect of it during his waking hours, then allow his unconscious mind to work on it while he slept. He trusted his dreams to show him solutions that his conscious reasoning couldn't reach. This makes Tesla's story particularly fascinating from a modern perspective. We now know that the brain continues processing information during sleep, making connections and solving problems in ways that are different from waking consciousness. Tesla seemed to have intuited this long before neuroscience could explain it. The alternating current system that powers your home, charges your phone, and runs every electrical device in your life can be traced back to a Serbian genius having dreams about spinning wheels of light. Every time you flip a light switch, you're benefiting from insights that came to Tesla through his sleeping mind. Can you imagine if we all had Tesla's ability to dream technical solutions? Instead of lying awake worrying about problems, we'd be unconsciously designing revolutionary inventions. Though, knowing my luck, I'd probably just dream about improved ways to untangle Christmas lights or figure out which USB cable goes with which device. But Tesla's story suggests that there might be incredible potential hidden in our own dreams, waiting for us to pay attention and take them seriously. Maybe the next great technological breakthrough is floating around in someone's unconscious mind right now, just waiting for the right dreamer to wake up and write it down. Now let's talk about Dmitry Mendeleev, a Russian chemist with a beard so magnificent it probably had its own gravitational field and definitely required its own postal code. This is the story of how the periodic table, that chart of elements that haunted your high school chemistry class, came to Mendeleev through a dream so perfectly organized that it makes. Marie Kondo's organizational skills look like amateur hour. But before we dive into Mendeleev's world, changing dream, let me paint you a picture of what chemistry was like in 1869. Imagine trying to organize the world's most chaotic library. where the books keep changing size. Some of them are written in languages that don't exist yet. And oh, by the way, about half the books haven't been written yet. That's essentially what chemists were facing when trying to make sense of the chemical elements. By 1869, scientists had discovered 63 different elements, each with its own unique properties, atomic weight, and chemical behavior. Some elements were metals, others were gases, some were incredibly reactive, others were completely inert. It was like having a collection of 63 completely different alien artifacts and trying to figure out how they all related to each other. Mendeleev himself was quite the character. Born in Siberia as the youngest of somewhere between 11 and 17 children, because apparently record-keeping in 19th century Russia was as chaotic as their chemistry, he showed an early talent for mathematics and science. His father went blind when Dmitri was young, and his mother ran a glass factory to support the family. So Mendeleev literally grew up around the chemistry of glass, watching elements combine and transform in the furnaces. What made Mendeleev different from other chemists of his time was his obsession with patterns. While most chemists were content to study individual elements in isolation, Mendeleev was convinced that there had to be some underlying order to the chaos. He believed that the elements weren't just random collections of atoms. They were part of a greater system that followed natural laws. This wasn't just scientific intuition, it was almost mystical conviction. Mendeleev would spend hours staring at lists of elements, looking for hidden relationships. He was like a cosmic detective, convinced that the universe had left clues about its fundamental structure and the properties of chemical elements. The problem was that nobody could figure out what that pattern was. Scientists had tried arranging elements by atomic weight, by chemical properties, by physical characteristics, by when they were discovered, by how hard they were to pronounce. Nothing worked. Every organizational system would get most of the elements right, but there would always be glaring exceptions that broke the pattern. Mendeleev's study in St. Petersburg was a testament to his obsession. The walls were covered with charts, graphs, and lists of elements arranged in every conceivable way. He had index cards for each element with their properties written out in meticulous detail. He would spend entire nights shuffling and reshuffling these cards, looking for the pattern that would make everything fall into place. Picture this bearded Russian genius, surrounded by mountains of paper in a room lit by flickering candles, trying to solve a puzzle that had stumped every chemist in the world. His colleagues probably thought he was losing his mind, spending months on what seemed like an impossible organizational task, when there were so many other chemical mysteries to explore, but Mendeleev couldn't let it go. He had this absolute conviction that the elements were trying to tell him something, that there was a hidden order just waiting to be discovered. He would arrange and rearrange his element cards for hours, like a fortune teller trying to read the future in a deck of chemical cards. For weeks leading up to his breakthrough, Mendeleev had been getting tantalizingly close to something. He could see that elements with similar properties seemed to recur at regular intervals when arranged by atomic weight. Lithium, sodium, and potassium all had similar chemical behaviors. So did fluorine, chlorine, and bromine. The pattern was almost there, but not quite right. The problem was that the atomic weights didn't quite line up. If you arranged elements strictly by atomic weight, the chemical properties would go haywire. But if you arranged them by chemical properties, the atomic weights would be random. It was like trying to solve a jigsaw puzzle where the pieces kept changing shape. Mendeleev had been working on this problem obsessively for months. He would stay up until dawn, rearranging his element cards, making lists, drawing charts, and getting increasingly frustrated. He knew the answer was there somewhere. He could feel it, but it remained just beyond his grasp. The night of February 17, 1869, Mendeleev had been working on his periodic system for 3 days straight without sleep. He was exhausted, frustrated, and beginning to doubt whether the pattern he was seeking actually existed. His study was a chaos of papers, his element cards were scattered across every surface, and his magnificent beard was probably in desperate need of maintenance. Finally, sometime in the early morning hours, Mendeleev fell asleep at his desk, his head resting on a pile of chemical calculations. And that's when his subconscious decided to become the world's greatest chemistry teacher. In his dream, Mendeleev saw a table, not just any table, but a perfectly organized chart where every single element fell into its correct place. It was like watching the universe reveal its secret filing system, as if the cosmic librarian had finally decided to show him how the books were supposed to be arranged. The table in his dream was breathtakingly elegant. Elements were arranged in rows and columns based on their atomic weights, but the arrangement also grouped elements with similar properties in the same columns. It was a perfect marriage of numerical order and chemical logic. The pattern that had been eluding him for months was suddenly crystal clear. But here's where the dream gets really extraordinary. Mendeleev's sleeping brain didn't just organize the 63 known elements. It created a table with blank spaces where unknown elements should exist. His dream was essentially predicting the future of chemistry, showing him elements that hadn't been discovered yet. The dream table was incredibly detailed. Mendeleev could see not just where the unknown elements belonged, but what their properties should be. He could visualize their atomic weights, their chemical behaviors, their physical characteristics. It was like having a cosmic cheat sheet for elements that didn't exist yet. When Mendeleev woke up, he immediately grabbed a pen and started writing down everything he could remember from his dream. The table that emerged on his paper was almost identical to what he had seen while sleeping. And except for one element that needed to be corrected, tellurium and iodine needed to be swapped, everything from his dream was exactly right. The periodic table that Mendeleev wrote down that morning is essentially the same one that hangs in every chemistry classroom in the world today. The fundamental structure, the arrangement of elements, the prediction of unknown elements, it all came from that single night's dream. But the real proof of his dream's accuracy came over the following years. Mendeleev had predicted the existence of several unknown elements based on the gaps in his dream table. He didn't just predict that these elements existed, he described their properties in extraordinary detail. For example, he predicted an element he called Eka, aluminum, an element that should exist in the same column as aluminum but with different properties. He predicted its atomic weight, 68, its density, 5. 9 grams per cubic centimeter, its melting point, low, and its chemical behavior, it should form compounds similar to aluminum but with different properties. People thought he was crazy. Here was this Russian chemist claiming that elements existed based on a dream-inspired table, and he was describing their properties with scientific precision. It was like a meteorologist predicting next week's weather based on tea leaves. But then, in 1875, a French chemist named Paul Émile Lecoq de Boisbaudran discovered gallium, and its properties matched Mendeleev's predictions almost exactly. The atomic weight was 69.7 instead of 68. The density was 5.9 grams per cubic centimeter, exactly as predicted, and its chemical behavior was precisely what Mendeleev had described. This wasn't just luck, it was like having a direct hotline to the fundamental structure of matter. Mendeleev had dreamed about an element that didn't exist, described its properties in detail, and then chemistry proved him right. The same thing happened with scandium in 1879 and germanium in 1886. Each newly discovered element fit perfectly into Mendeleev's dream table, with properties that matched his predictions with uncanny accuracy. It was as if the universe had shown him the instruction manual for atomic structure. Think about that for a moment. A guy fell asleep at his desk and dreamed about chemical elements that didn't exist yet, then accurately predicted their properties based on nothing but the pattern he saw in his sleep. That's not just scientific intuition, that's like having access to the source code of reality itself. The periodic table isn't just a useful tool for chemists, it's literally the blueprint for understanding how atoms work. Every chemical reaction, every material property, every atomic behavior can be explained using the patterns that Mendeleev saw in his dream. The table reveals the underlying mathematical structure of matter itself. What makes this story even more remarkable is how Mendeleev's dream table anticipated discoveries that wouldn't be made for decades. The periodic table predicted the existence of noble gases before they were discovered. It explained why certain combinations of elements were stable while others were reactive. It provided a framework for understanding atomic structure before anyone knew what the inside of an atom looked like. The dream that came to Mendeleev that night in 1869 was so accurate that it's still used today, over 150 years later. We've discovered dozens of new elements since then, artificial elements created in particle accelerators, super heavy elements that exist for only fractions of a second, and every single one fits perfectly into the pattern his sleeping brain revealed. Modern quantum mechanics has shown that the periodic table reflects the fundamental structure of atoms, the arrangement of electrons in shells and subshells that determine chemical properties. Mendeleev's dream somehow anticipated quantum mechanical principles that wouldn't be discovered for another 50 years. But here's what I find most fascinating about Mendeleev's story. His dream didn't just solve the problem of organizing known elements, it revealed the mathematical structure underlying all possible elements. The periodic table is essentially a map of atomic possibility, showing not just what elements exist, but what elements can exist. Mendeleev's dream table showed him that the properties of elements are not random, but follow predictable patterns based on atomic structure. This insight transformed chemistry from a collection of isolated facts into a unified science based on underlying principles. The periodic table has become one of the most important scientific achievements in human history. It's used in every chemistry lab, every materials science program, every nuclear physics experiment. It's the foundation for understanding how atoms combine to form molecules, how materials get their properties, and how the universe builds complexity from simple elements. It makes you wonder what other fundamental patterns of reality might be floating around in our unconscious minds, just waiting for the right dreamer to wake up and write them down. Maybe the theory of everything is just a good night's sleep away, hiding in someone's dream like Mendeleev's periodic table was hiding in his. Let's shift gears to Denmark, where a young physicist named Niels Bohr was having the kind of dreams that would make quantum mechanics seem almost reasonable, which, if you know anything about quantum mechanics, is saying something. This is the story of how our modern understanding of atomic structure came from a dream so cosmically bizarre that it involved sitting on the surface of the sun having casual conversations with orbiting electrons. But before we dive into Bohr's world, changing solar dream, let me set the stage for what atomic physics was like in 1930. This was the scientific equivalent of the Wild West, where cowboys were replaced by physicists and shootouts were replaced by theoretical arguments about the nature of reality. Scientists had recently discovered that atoms weren't tiny solid balls as previously thought, but complex structures with moving parts, and nobody could figure out how the hell they actually worked. Niels Bohr himself was a fascinating character, a Danish physicist who combined the methodical precision of Scandinavian thinking with an almost mystical intuition about the behavior of matter. He was tall, lanky, and had this habit of mumbling complex theoretical insights while walking around in circles, which probably made him look like a mad scientist to casual observers. Born in Copenhagen in 1885, Bohr grew up in an intellectual family where dinner conversation probably included discussions about the fundamental nature of reality. His father was a physiology professor, his mother came from a family of educators, and young Niels showed early signs of being able to think about problems in ways that other people found either brilliant or completely insane. What made Bohr special wasn't just his intelligence, it was his ability to visualize abstract physics concepts in concrete, almost childlike ways. While other physicists got lost in mathematical equations, Bohr would imagine atoms as tiny solar systems, electrons as planets, and chemical bonds as cosmic forces. This kind of thinking drove his more mathematically minded colleagues crazy, but it also allowed him to see patterns that pure mathematics might miss. In 1913, Bohr was working in England under Ernest Rutherford, the New Zealand physicist who had recently discovered that atoms have a dense central nucleus surrounded by electrons. This was revolutionary stuff instead of being solid balls. Atoms were mostly empty space with a tiny, dense center and electrons somehow orbiting around it. But there was a massive problem with this model. According to classical physics, electrons orbiting the nucleus should continuously emit electromagnetic radiation, lose energy, and spiral into the center in a fraction of a second. This would mean that all atoms should collapse instantly. Matter shouldn't exist, and the universe should be a uniform soup of collapsed atomic debris. Since atoms obviously weren't collapsing, because matter exists and we're all still here, something was fundamentally wrong with classical physics. It was like discovering that, according to all known laws of aerodynamics, bumblebees shouldn't be able to fly. Except instead of bumblebees, it was the entire physical universe. Bohr had been puzzling over this paradox for months. How could electrons orbit the nucleus without losing energy and spiraling inward? What kept atoms stable? It was like trying to understand how planets could orbit the sun if gravity worked completely differently than expected, except the consequences were even more mind-bending. The scientific community was essentially stuck. They knew that atoms had nuclei and electrons, they knew that atoms were stable, but they couldn't explain how these two facts could coexist. It was one of those situations where experimental reality and theoretical understanding were completely at odds with each other. Bohr had tried every approach he could think of. He'd studied Rutherford's experimental data, analyzed the mathematical equations, consulted with other physicists, and generally driven himself nearly insane trying to reconcile the contradictions. The problem seemed unsolvable using conventional physics. For weeks before his breakthrough, Bohr had been having unusually vivid dreams about cosmic scenarios. These weren't abstract physics dreams. They were incredibly detailed visions where he found himself in various astronomical situations. Sometimes he was floating in space watching stars form. Sometimes he was riding on comets. Sometimes he was observing the birth of galaxies from a cosmic balcony. But the most important dream came on a night when Bohr had fallen asleep while reading about planetary motion. In this dream, he found himself sitting on the surface of the sun, not burning up, just casually relaxing on the surface of a star like it was a warm beach chair on the world's most extreme vacation. The dream was incredibly vivid and detailed. Bohr could feel the immense heat and energy of the sun beneath him, but somehow he was completely comfortable and protected. Around him, the solar atmosphere was alive with electrical activity. Streams of charged particles flowing in complex patterns, magnetic fields twisting and dancing, energy radiating outward in all directions. But the most remarkable part of the dream was what was orbiting around him. Instead of planets, Bohr was surrounded by electrons, but these weren't tiny particles. In his dream, the electrons appeared as glowing spheres of various sizes and colors, each one following a perfect circular path at specific distances from where he sat. The dream electrons were absolutely beautiful. Each one pulsed with its own inner light, creating trails of energy as they moved through their orbits. Some were close to Bohr's solar perch, zipping around in tight, fast circles. Others were farther away, moving more slowly in larger orbits. Each electron seemed to know exactly where it belonged. What made the dream truly extraordinary was that Bohr could see something that wasn't supposed to be possible according to classical physics. The electrons weren't continuously radiating energy. Instead of spiraling inward as they should have according to conventional theory, they were locked into stable, fixed orbits. In the dream, Bohr could see that the planets could only exist at certain orbital distances. They couldn't spiral inward or drift outward freely. They were locked into specific energy levels, like seats on a cosmic Ferris wheel. An electron could jump from one level to another, but it couldn't exist between levels. This was the key insight that had been eluding physicists. Energy wasn't continuous, but came in discrete packets. The electrons in Bohr's dream were demonstrating what would later be called quantum behavior, where only certain energy states were allowed. The dream became even more fascinating when Bohr watched electrons jumping between orbits. When an electron jumped from a higher orbit to a lower one, it would emit a burst of light with a specific color and energy. When it jumped from a lower orbit to a higher one, it would absorb light of exactly the same energy. It was like watching a cosmic light show where each color had a specific meaning. Bohr could see that this jumping behavior explained something that had been puzzling scientists for decades: why atoms emit and absorb light at specific frequencies. The dream was showing him that atomic spectra, the fingerprint patterns of light that different elements produce, were actually maps of the electron energy levels within atoms. When Bohr woke up from this solar dream, he realized that his sleeping mind had shown him the solution to one of physics' greatest puzzles. Electrons don't continuously lose energy because they can only exist in discrete energy states. They orbit the nucleus like planets, but only at specific allowed distances. This was revolutionary thinking that violated everything scientists thought they knew about energy and motion. Classical physics said that energy was continuous and could take any value. Bohr's dream-inspired model said that at the atomic level, energy came in discrete chunks, quanta, and electrons could only possess certain specific amounts of energy. Bohr immediately began working out the mathematical details of what he had seen in his dream. His calculations showed that an electron's energy was directly related to its orbital distance from the nucleus. Electrons in higher orbits had more energy, electrons in lower orbits had less energy, and the energy differences between levels determined the color of light that would be emitted or absorbed when electrons jumped between orbits. The Bohr atomic model, directly inspired by his dream of sitting on the sun, explained a whole range of previously mysterious phenomena. It explained why atoms were stable, electrons couldn't spiral into the nucleus because they were confined to specific energy levels. It explained atomic spectra. The colors of light emitted by different elements corresponded to the energy differences between electron levels. It explained chemical bonding. Atoms could share or transfer electrons between their allowed energy states. But most importantly, Bohr's dream-inspired model introduced the concept of quantization into physics. The idea that energy comes in discrete packets rather than continuous amounts became one of the foundational principles of quantum mechanics. What Bohr saw in his solar dream was the beginning of our modern understanding of how the quantum world operates. The really remarkable thing about Bohr's dream is how it combined the familiar with the impossible in exactly the right way to reveal new physics. The image of electrons orbiting like planets was familiar enough to be understandable, but the idea of sitting on the sun and watching quantized energy levels was impossible enough to break free from classical thinking. Bohr's model wasn't just theoretically elegant, it made specific, testable predictions. It predicted the exact wavelengths of light that hydrogen atoms should emit and absorb, and these predictions matched experimental observations with remarkable precision. It was like his dream had given him a user manual for the hydrogen atom. The success of Bohr's atomic model launched the quantum revolution in physics. His insight that energy is quantized at the atomic level became the foundation for understanding all atomic and molecular behavior. Every laser, every computer chip, every LED light, every piece of modern electronics depends on principles that Bohr first glimpsed while dreaming about sitting on the sun. But perhaps most importantly, Bohr's dream showed that sometimes the most profound scientific insights come from thinking, in ways that seem completely impossible by everyday standards. You can't understand quantum mechanics by thinking like classical physics. You need the kind of impossible logic that only appears in dreams. Bohr later said that his dream helped him understand that the atomic world operates by different rules than our everyday experience. At the scale of atoms and electrons, the familiar concepts of continuous motion and energy don't apply. Instead, nature behaves in discrete, quantized ways that our intuition finds difficult to grasp. The atomic model that emerged from Bohr's solar dream became the stepping stone to full quantum mechanics. While later physicists like Schrödinger and Heisenberg would develop more sophisticated mathematical descriptions of atomic behavior, they were all building on the fundamental insight that Bohr received while lounging on the surface of the sun. What I find most amazing about this story is how Bohr's impossible dream scenario, sitting comfortably on a star, was exactly the right kind of impossible thinking needed to understand atomic physics. Sometimes the universe reveals its deepest secrets through the strangest possible methods, using dream logic to communicate truths that rational thinking can't reach. It makes you wonder what other fundamental insights about reality might be hiding in our own impossible dreams, waiting for someone brave enough to take them seriously and work out the implications. Maybe the next great breakthrough in physics is floating around in someone's unconscious right now, disguised as just another weird dream about hanging out in cosmically impossible places. Our final main story takes us to colonial India, where a self-taught mathematical genius named Srinivasa Ramanujan was receiving formulas directly from a Hindu goddess in his dreams. And before you think this sounds too mystical for serious science, remember that Ramanujan's goddess-delivered mathematics are still being studied, applied, and occasionally causing mathematicians to question their life choices over a century later. This is perhaps the most extraordinary story in our collection tonight, because it involves not just scientific breakthrough through dreams, but the intersection of ancient spiritual traditions with cutting-edge mathematics. It's like if Stephen Hawking had received his insights about black holes from conversations with ancient Greek gods, except the mathematics actually worked perfectly. But before we dive into Ramanujan's divine mathematical dreams, let me paint you a picture of what his world was like. Born in 1887 in Erode, a small town in southern India, Ramanujan grew up in poverty during the height of British colonial rule. His family belonged to the Brahmin caste, which traditionally emphasized learning and scholarship, but they had very little money and even less access to formal education. Ramanujan's mathematical genius emerged in the most unlikely circumstances. His family couldn't afford books, proper schooling, or any of the resources that mathematical education normally requires. The entire foundation of his mathematical knowledge came from a single textbook, a synopsis of elementary results in pure and applied mathematics by George Carr, which was basically a collection of mathematical formulas without explanations or proofs. Imagine learning mathematics from a book that's essentially just a list of equations with no context, no derivations, and no explanations. It's like trying to learn to cook from a recipe book that only lists ingredients without any instructions. Most people would find it completely useless, but Ramanujan somehow used this bare bones mathematical reference to teach himself advanced mathematics that most professional mathematicians struggle with. What made Ramanujan's situation even more remarkable was that he had no access to the mathematical community. There were no universities nearby, no mathematics professors to consult, no libraries full of mathematical journals. He was essentially developing advanced mathematical insights in complete intellectual isolation, like a lone explorer mapping unknown territories with only the most basic tools. Ramanujan himself was a deeply spiritual person who saw mathematics not as an abstract intellectual exercise, but as a window into the divine structure of reality. He was a devout Hindu who believed that mathematics was a language through which the gods communicated with humanity. This perspective, which would seem completely foreign to most Western mathematicians, was fundamental to how he approached mathematical problems. The goddess who appeared in Ramanujan's dreams was Namagiri, a form of the Hindu goddess Lakshmi who was particularly revered by his family. Namagiri was considered the family deity, a divine protector who watched over the household and provided guidance during difficult times. For Ramanujan, this goddess became his mathematical mentor, appearing in his dreams to reveal formulas and theorems. The dream visits from Namagiri began when Ramanujan was still a teenager, struggling to understand mathematics beyond what his single textbook could teach him. He would spend his days working on mathematical problems, filling slate after slate with calculations and formulas, then fall asleep exhausted from mental effort. That's when the goddess would appear. In these dreams, Namagiri would manifest as a beautiful woman dressed in brilliant red clothing, radiating a warm, golden light that seemed to illuminate the mathematical concepts she was teaching. She would speak to Ramanujan in Tamil, his native language, but the mathematical formulas she showed him were written in golden symbols that seemed to hover in the air around her. The goddess didn't just show Ramanujan formulas, she would demonstrate their truth through visual proofs that unfolded like cosmic animations. He could see infinite series converging to precise values, watch mathematical functions transform into geometric patterns, observe the deep connections between apparently unrelated mathematical concepts. What made these dreams extraordinary wasn't just their mathematical content, but their incredible detail and precision. Ramanujan would wake up and immediately write down complex formulas involving infinite series, continued fractions and number theory relationships that looked correct but were far beyond what anyone expected from a self-taught mathematician in colonial India. The most famous example of Ramanujan's goddess delivered mathematics is his formula for calculating pi with extraordinary precision. In one of his dreams, Namagiri showed him an infinite series that could compute pi to any desired accuracy using a pattern involving factorials and square roots. The formula looked almost magical, a beautiful arrangement of mathematical symbols that seemed to encode the very essence of circular geometry. When Ramanujan first wrote down this pi formula, mathematicians didn't know what to make of it. The series converged incredibly rapidly, meaning you could get highly accurate values of pi using relatively few terms. Modern computer algorithms still use variations of Ramanujan's pi formula because it's so much more efficient than other methods. But here's what makes this story absolutely mind-bending. Ramanujan couldn't prove most of his goddess-delivered formulas. When asked to explain how he had discovered a particular result, he would simply say that Namagiri had shown it to him in a dream. He would describe the visual demonstration the goddess had provided, but he couldn't translate her divine pedagogy into the formal mathematical proofs that Western mathematics required. This drove Western mathematicians absolutely crazy. Here was this untrained clerk from India producing formulas that looked correct, but couldn't be proven using known mathematical techniques. It violated everything they understood about how mathematical research was supposed to work. Mathematics was supposed to be logical, systematic, and based on rigorous proof, not mystical revelations from Hindu goddesses. When Ramanujan's work first came to the attention of British mathematicians, many dismissed it as the confused scribblings of an amateur who didn't understand proper mathematical rigor. His notebooks were filled with formulas that seemed to come from nowhere, stated without proof or explanation. It looked like mathematical poetry rather than serious mathematics. But then mathematicians started checking his formulas, and they kept turning out to be correct. Not just approximately correct, precisely, exactly, perfectly correct. Ramanujan's goddess-delivered mathematics was producing results that matched the most sophisticated mathematical techniques available, but through methods that nobody could understand. The breakthrough came when Ramanujan's work reached G.H. Hardy, a prominent mathematician at Cambridge University. Hardy was known for his extremely rigorous approach to mathematics. He believed that mathematical beauty and truth had to be proven through logical argument, not intuition or inspiration. He was about as far from mystical as a mathematician could be. When Hardy first saw Ramanujan's work, he later said it was like nothing he had ever encountered. The formulas were so unusual and so profound that they couldn't possibly be the work of a mathematical amateur. Either this unknown Indian clerk was a mathematical genius of extraordinary ability, or he was completely insane. There was no middle ground. Hardy spent months trying to understand and verify Ramanujan's results. Many of the formulas required mathematical techniques that were at the cutting edge of early 20th century mathematics. Some couldn't be proven at all using the methods available at the time. Yet when Hardy could check them numerically, they were always correct. The most spooky part of Ramanujan's story is that many of his goddess-delivered formulas turned out to anticipate mathematical developments that didn't occur for decades. His work on partition functions, Mach theta functions, and infinite series predicted areas of mathematics that wouldn't be fully developed until the computer age. For example, Ramanujan's formulas for partition functions, ways of writing numbers as sums of positive integers, revealed deep patterns in number theory that mathematicians are still discovering today. His work anticipated connections between number theory and modular forms that weren't fully understood until the 1970s. Similarly, his mysterious Mach theta functions, mathematical objects that the goddess showed him in dreams, remained largely incomprehensible until recent decades. Modern mathematicians have discovered that these functions are related to quantum invariance in string theory, areas of mathematics that didn't exist when Ramanujan was alive. It's as if Namagiri was showing Ramanujan a mathematical library that wouldn't be built for another century. His dreams were accessing mathematical knowledge that was decades ahead of its time, revealing patterns and relationships that the mathematical community wasn't ready to understand. When Ramanujan was finally invited to Cambridge University in 1914, his collaboration with Hardy became one of the most extraordinary partnerships in mathematical history. Hardy, the rigorous logician, working with Ramanujan, the mystical visionary, to understand and prove the formulas that the goddess had revealed in dreams. Hardy later wrote that working with Ramanujan was like having access to a mathematical oracle. Ramanujan would produce results that seemed impossible, but when Hardy could verify them, they were always correct. It was as if Ramanujan had a direct line to mathematical truth that bypassed the usual methods of discovery and proof. The cultural dimension of this story is particularly fascinating. Ramanujan lived in a tradition where receiving knowledge through divine dreams was considered normal and valuable. In Hindu philosophy, the boundary between the human mind and divine consciousness is much more permeable than in Western thought. Ramanujan never questioned whether his mathematical visions were real. He just trusted what the goddess showed him and wrote it down. This cultural context may have been crucial to Ramanujan's mathematical success. While Western mathematicians were trained to doubt and question every mathematical insight, Ramanujan was trained to trust divine revelation. This allowed him to explore mathematical territories that more skeptical minds might have avoided. Ramanujan claimed that every formula the goddess showed him was tested in his dreams. If an equation was false, Namagiri would demonstrate its failure before presenting the correct version. It was like having a divine mathematics tutor who only worked the night shift, complete with quality control and error correction. The testing process in Ramanujan's dreams was apparently quite sophisticated. He would see mathematical objects behaving in ways that revealed their true nature. Infinite series would converge or diverge visually, geometric patterns would transform to show hidden symmetries, numerical relationships would be demonstrated through cosmic animations that made their truth obvious. What makes Ramanujan's story particularly remarkable is how his goddess delivered insights continue to influence mathematics today. His formulas appear in areas as diverse as computer science, physics, and cryptography. Mathematical concepts that Namagiri showed him in dreams over a century ago are now being used to solve problems in quantum mechanics, string theory, and computational mathematics. Modern number theorists regularly discover that some new mathematical result was actually anticipated by Ramanujan's dream formulas. It's become a running joke in certain mathematical circles that whenever you think you've discovered something new in number theory, you should check Ramanujan's notebooks first. He probably dreamed it decades ago. The partition function formulas that Ramanujan received from Namagiri are now used in statistical mechanics to understand phase transitions in physical systems. His infinite series are used in computer algorithms for high precision calculations. His Mach theta functions have found applications in quantum field theory and string theory. Perhaps most remarkably, some of Ramanujan's goddess-delivered formulas are still not fully understood. Modern mathematicians continue to discover new implications and applications of mathematical insights that came to him through dreams over a century ago. It's as if Namagiri downloaded an entire mathematical library into his unconscious mind, and we're still finding new books in the collection. In Western academic culture, claiming that a Hindu goddess taught you mathematics in dreams would probably end your career faster than plagiarizing your dissertation. But Ramanujan's formula filled dreams produced mathematical insights that continue to influence research today. Sometimes the most irrational seeming sources lead to the most rational results. The story of Ramanujan and Namagiri challenges our assumptions about how mathematical knowledge is discovered and validated. It suggests that mathematical truth might be accessible through channels that our rational, proof-based approach to mathematics doesn't recognize or value. It makes you wonder how many other brilliant mathematical insights might be floating around in the collective unconscious, just waiting for someone who's willing to listen to their dreams and write down what they see. Maybe the solution to the Riemann hypothesis is currently being dreamed by someone who's never heard of complex analysis. Maybe the unified field theory is being revealed to someone who thinks they're just having weird dreams about cosmic geometry. Ramanujan's story suggests that the universe might be more mathematically literate than we give it credit for, and that sometimes the deepest truths about reality are communicated through the strangest possible channels, like a Tamil clerk having conversations with a Hindu goddess who happens to be one of history's greatest mathematics teachers. In 1921, Otto Lowy was trying to prove something that seemed almost impossible to demonstrate, that nerve cells communicate using chemical signals rather than just electrical impulses. This was revolutionary thinking at the time, when most scientists believed the nervous system worked purely through electrical connections, like a biological telephone network where messages traveled as electrical currents through neural wires. Lowy himself was quite the character, an Austrian pharmacologist who had spent years studying how drugs affected the nervous system. He had this nagging suspicion that nerves didn't just send electrical signals but actually released chemical messengers that carried information from one cell to another. It was like proposing that telephone conversations happen not through electrical signals and wires, but through people whispering chemical messages to each other. The problem was that this chemical theory of nerve transmission was nearly impossible to prove with the technology available in 1921. Nerves are incredibly small. They work incredibly fast, and any chemical signals they might release would be in tiny quantities that disappeared almost instantly. It was like trying to prove that hummingbirds communicate by releasing invisible perfumes that only last for microseconds. Lowy had designed what he thought was an elegant experiment using frog hearts. The idea was beautifully simple: take 2 frog hearts, stimulate the vagus nerve of one heart to slow it down, collect the fluid around the stimulated heart, then transfer that fluid to the second heart to see if it would have the same effect. If nerve signals were chemical, the second heart should slow down as if its own vagus nerve had been stimulated. But every time Lowy tried this experiment, something would go wrong. The timing would be off, the hearts would stop beating entirely, the fluid transfer wouldn't work properly, or the results would be completely inconclusive. It was like trying to perform surgery with boxing gloves while blindfolded during an earthquake. The technique required absolutely perfect timing. The vagus nerve had to be stimulated at exactly the right moment. The fluid had to be collected immediately, and the transfer had to happen within seconds before any chemical signals degraded. Lowy was beginning to think that maybe his colleagues were right, and the chemical theory of nerve transmission was just wishful thinking. For months, Lowy struggled with this experiment. He would spend entire days in his laboratory, working with frog hearts until his hands were stained with preservation fluid, and his lab coat looked like he'd been performing autopsies on amphibians. His colleagues probably thought he was losing his mind, obsessing over an experiment that clearly wasn't working. But then, on the night of Easter Sunday in 1921, Lowy had one of the most important dreams in the history of neuroscience. In this dream, he saw his frog heart experiment performed with absolutely perfect technique. Every step executed flawlessly, every timing interval precise, every procedure optimized for success. The dream was incredibly detailed and practical. Lowy could see exactly how to position the hearts, precisely when to stimulate the vagus nerve, exactly how to collect the fluid, and the perfect timing for transferring it to the second heart. It was like watching a masterclass in experimental technique performed by an invisible neuroscience professor. But what made the dream truly extraordinary was that Lowy could see the chemical signals themselves. In his dream, the stimulated heart released a cloud of chemical messengers that looked like golden particles floating in the fluid. These particles carried the nerve signal, and when they reached the second heart, they delivered the message to slow down. When Lowy woke up the next morning, he immediately wrote down everything he could remember from his dream. Then he rushed to his laboratory and performed the exact experiment he'd dreamed about, following every detail of the technique his sleeping mind had shown him. This time, everything worked perfectly. The fluid from the stimulated heart caused the second heart to slow down dramatically, proving conclusively that nerve cells communicate through chemical messengers rather than just electrical signals. The experiment that had failed dozens of times suddenly worked flawlessly, following the protocol that came to him in a dream. This dream-guided experiment earned Lowy the Nobel Prize in Physiology in 1936. and it fundamentally changed our understanding of how the nervous system works. The chemical messengers that Lowy discovered became known as neurotransmitters, substances like acetylcholine, dopamine, and serotonin that carry signals between nerve cells. The implications of Lowy's discovery were enormous. Every antidepressant medication works by affecting neurotransmitter levels. Every treatment for Parkinson's disease targets the dopamine system. Every understanding of how the brain processes information depends on the chemical communication between neurons that Lowy first demonstrated with his dream-inspired frog heart experiment. But here's what I find most fascinating about this story. Lowy later admitted that if he'd tried to plan this experiment while awake, he probably would have talked himself out of it. The procedure seemed too delicate, too dependent on perfect timing, too likely to fail. Only in a dream did it seem obviously doable. It's like his conscious mind was too smart for his own good, overthinking a procedure that his subconscious knew would work perfectly. His rational brain was creating obstacles that his dreaming brain simply ignored. Sometimes the biggest barrier to scientific breakthrough is our own skepticism about whether our ideas will actually work. The really remarkable thing about Lowy's dream is how it provided not just the general concept of chemical neurotransmission, but the specific experimental technique needed to prove it. His sleeping brain had apparently been running laboratory simulations, working out all the practical details of timing, positioning, and procedure that his conscious mind had been unable to solve. This suggests that our unconscious minds might be much better at solving practical problems than we give them credit for. While our conscious thoughts get bogged down in doubts and complications, our sleeping brains might be running clean, efficient simulations that find optimal solutions. Lowy's discovery opened up entirely new fields of research. Pharmacology became focused on understanding how drugs affect neurotransmitter systems. Psychiatry began to understand mental illness in terms of chemical imbalances in the brain. Neuroscience evolved from studying electrical signals to studying the complex chemical conversations that happen between neurons. The funny thing is that Lowy's dream-inspired experiment was so simple and elegant that it's now taught in introductory neuroscience courses. Students learn about Lowy's experiment as a classic demonstration of chemical neurotransmission without realizing that the experimental design came from a dream that solved a problem that had stumped one of the world's leading neuroscientists. It makes you wonder how many other scientific breakthroughs might be just a good night's sleep away. Maybe every researcher should keep a dream journal next to their lab notebook, ready to capture the experimental insights that their unconscious minds might provide. Maybe the solution to some of today's biggest scientific challenges is floating around in someone's dreams right now, waiting for the right person to wake up and write it down. Frederick Banting was a young Canadian surgeon who knew almost nothing about diabetes research when he had the dream. That would save millions of lives and transform him from a struggling small town doctor into one of medical history's most important figures. This was 1920, and diabetes was essentially a death sentence. Patients would waste away as their bodies couldn't process sugar, and there was no effective treatment beyond starvation diets that merely prolonged the inevitable. Picture this, a 29-year-old orthopedic surgeon in London, Ontario, trying to make ends meet with a medical practice so unsuccessful that some days he didn't see a single patient. Banting had returned from World War I with a Distinguished Conduct Medal and dreams of a successful medical career, but instead found himself struggling financially and professionally in a small Canadian town where patients seemed to prefer the older, more established doctors. Banting was not the kind of person you'd expect to revolutionize diabetes treatment. He had no background in biochemistry, no experience with metabolic diseases, and no research funding. His medical school grades were mediocre at best, and his surgical practice was barely keeping him afloat financially. By any reasonable measure, he was probably the least qualified person in Canada to attempt groundbreaking diabetes research. But sometimes being an outsider is an advantage. Banting wasn't limited by conventional wisdom about what wouldn't work in diabetes research. He hadn't spent years learning all the reasons why previous attempts to extract anti-diabetic substances from the pancreas had failed. His ignorance of the field's established failures made him willing to try approaches that more experienced researchers had already dismissed. The night that changed everything started with Banting reading a single article about diabetes research before falling asleep. The article, published in Surgery, Gynecology, and Obstetrics, discussed the mysterious islets of Langerhans, special cells scattered throughout the pancreas that might produce some kind of anti-diabetic substance. The article explained that scientists had been trying for years to extract this hypothetical anti-diabetic substance, but every attempt had failed because the pancreas also produces powerful digestive enzymes that destroy proteins during the extraction process. It was like trying to preserve a delicate flower while it's being attacked by molecular scissors. That night, as Banting dozed off with the medical journal still open on his chest, his subconscious began working on the problem that had stumped diabetes researchers for decades. In his dream, he saw a clear step-by-step procedure for extracting the anti-diabetic substance without destroying it in the process. The dream was remarkably specific and practical. Banting could see himself performing surgery on dogs, carefully tying off the pancreatic ducts, the tubes that carry digestive enzymes away from the pancreas. In the dream, he watched as the enzyme, producing cells, gradually withered away over several weeks, leaving behind only the islet cells that produce the anti-diabetic substance. What made the dream extraordinary was its precision. Banting could see the exact surgical technique, the optimal timing for extraction, and even the chemical processes that would preserve the active substance. His sleeping brain had apparently designed a complete research protocol that solved the fundamental problem of pancreatic enzyme destruction. When Banting woke up, he immediately wrote down a 25-word note that would become one of the most important sentences in medical history. Ligate pancreatic ducts of dogs. Wait 6 to 8 weeks for degeneration. Remove the residue and extract. This brief note, inspired by a dream, would become the protocol for discovering insulin. The beautiful irony of Banting's situation was that his lack of experience might have been exactly what was needed. More experienced researchers might have been intimidated by the complexity of pancreatic biochemistry or discouraged by the previous failures. Banting, in his naive enthusiasm, simply assumed that his dream protocol would work and set about making it happen. With remarkable persistence, Banting convinced the University of Toronto to give him laboratory space and a young medical student named Charles Best to help with the research. They worked in a hot, cramped laboratory during the summer of 1921, following Banting's dream protocol exactly despite having almost no funding and primitive equipment. The experimental procedure was exactly as Banting had dreamed it. They tied off pancreatic ducts in dogs, waited for the digestive tissue to degenerate, then extracted a brown, gooey substance from the remaining islet cells. The process was crude, labor-intensive, and produced an extract that looked more like muddy syrup than revolutionary medicine. But when they injected this crude extract into diabetic dogs, the results were nothing short of miraculous. The dogs' blood sugar levels dropped dramatically, and they regained strength and vitality. Animals that had been near death from diabetes suddenly became healthy and active. Banting and Best had created the world's first successful diabetes treatment. The first human patient to receive insulin was a 14-year-old boy named Leonard Thompson, who was dying of diabetes in Toronto General Hospital. He weighed only 65 pounds, was slipping in and out of consciousness, and his doctors expected him to die within days. The initial injection of Banting's crude insulin extract didn't work well. It was too impure and caused severe allergic reactions. But after the biochemist James Collip refined the extraction process, Thompson's condition improved dramatically. Within weeks, he had gained weight, regained strength, and returned to a normal, active life. The transformation was so remarkable that nurses and doctors wept openly when they saw the dying boy return to health. Word of the insulin discovery spread rapidly through the medical community. Within months, insulin was being produced commercially and distributed worldwide. Children who had been wasting away in hospital beds were returning to school and play. Parents who had been preparing for their children's deaths were instead planning for their futures. The discovery earned Banting and his collaborator John MacLeod the Nobel Prize in Physiology or Medicine in 1923, making Banting the youngest Nobel laureate in that category at age 32. However, Banting insisted on sharing his prize money with Charles Best, who had been excluded from the official recognition despite his crucial contributions to the research. But beyond the accolades and recognition, Banting's dream, inspired discovery fundamentally changed the experience of diabetes from a death sentence to a manageable condition. Millions of people who would have died from diabetes have lived full, productive lives because of the treatment protocol that came to Banting in a single night's dream. What I find most remarkable about this story is how a single night's sleep transformed an inexperienced surgeon into one of medical history's most important researchers. Banting's dream didn't just suggest a research direction, it provided a complete experimental protocol that worked exactly as envisioned. The insulin discovery also demonstrates how breakthrough medical research sometimes requires thinking outside established expertise. The diabetes specialists of 1920 knew too much about why pancreatic extracts didn't work. Banting's naive optimism, combined with his dream-inspired protocol, allowed him to attempt what more experienced researchers had concluded was impossible. Today, insulin therapy has evolved far beyond Banting's crude pancreatic extracts. Modern synthetic insulins are precisely engineered, delivered through sophisticated pumps and monitoring systems, and allow diabetic patients to live essentially normal lives. But every diabetic who injects insulin, every glucose monitor that checks blood sugar, every diabetes treatment protocol traces its origins back to that night when a struggling Canadian surgeon dreamed about tying off pancreatic ducts. It makes you think about how many other medical breakthroughs might be hidden in the dreams of people who don't even realize they're having revolutionary ideas while they sleep. Maybe the cure for cancer is floating around in someone's unconscious right now, waiting for the right dreamer to wake up and write down the protocol. Maybe the solution to Alzheimer's disease will come to a medical student who thinks they're just having a weird dream about brain chemistry. While everyone knows that Watson and Crick discovered the double helix structure of DNA, fewer people know about the recurring dreams that helped Watson visualize how the genetic code actually worked. This wasn't just about the physical structure, it was about understanding how information could be stored and copied in molecular form, essentially figuring out how life maintains its instruction manual across generations. James Watson was a young, ambitious American scientist working at the Cavendish Laboratory in Cambridge in the early 1950s. He was brash, confident, and absolutely obsessed with solving what he considered the most important puzzle in biology: how genetic information was stored and transmitted. Watson had this burning conviction that whoever cracked the DNA code would essentially understand the secret of life itself. But here's the thing about Watson: he wasn't primarily a chemist or a physicist. He was a biologist who understood genetics and evolution, but sometimes struggled with the complex three-dimensional molecular structures that his Cambridge colleagues took for granted. While his lab partner Francis Crick was brilliant at visualizing molecular geometry, Watson often found himself trying to understand DNA through more intuitive, almost storytelling approaches. In the months after publishing their famous DNA structure paper in 1953, Watson became obsessed with a question that kept him awake at night: how does DNA actually work? Sure, they'd figured out that it was a double helix with complementary base pairs, but how did this elegant structure function as a blueprint for life? How could a molecule carry instructions for building entire organisms? Watson started having the most extraordinarily vivid dreams about DNA, but these weren't abstract scientific visions. They were like molecular movies where he could watch the genetic process happening in real time. In these dreams, DNA appeared as a twisted ladder where each rung was a letter in some cosmic alphabet, and Watson could see how these molecular letters arranged themselves to spell out the instructions for life. The dreams were remarkably detailed and consistent. Watson would find himself shrunk down to molecular size, walking along the spiral backbone of DNA like climbing a twisted staircase. Each step revealed another base pair, adenine paired with thymine, guanine paired with cytosine, and he could see how these chemical letters formed words, sentences, and entire paragraphs of genetic information. But the most important aspect of Watson's dreams was watching DNA replication in action. In his dreams, he could observe the double helix untwisting and splitting apart, creating two single strands. Then he would watch as each strand served as a template for building a new complementary strand, with the molecular letters pairing up according to the base, pairing rules he and Crick had discovered. The replication process in Watson's dreams was like watching a molecular printing press. The DNA strands would separate, revealing the genetic text, and then cellular machinery would move along each strand, reading the letters and assembling matching copies. It was precise, elegant, and absolutely mesmerizing to watch at the molecular level. What made these dreams particularly valuable was that Watson could see the mutation process happening in real time. In his dreams, he would occasionally observe what he called molecular typos, situations where the wrong letter would be inserted during replication, changing the genetic message. These weren't random errors, but specific changes that he could watch happening and follow through their consequences. Watson's dream insights about mutations were remarkably prescient. He could see how a single letter change in the genetic code could alter the meaning of an entire genetic sentence, potentially changing the characteristics of an organism. This dream-level understanding of how genetic mutations worked helped establish the conceptual foundation for understanding evolution, genetic diseases, and eventually genetic engineering. The dreams also showed Watson something that wouldn't be fully appreciated for years, that DNA wasn't just a static storage medium, but a dynamic, interactive system. In his dreams, he could see how different sections of DNA could be turned on or off, how genes could interact with each other, and how the same genetic information could be interpreted differently in different cellular contexts. One particularly important dream showed Watson how DNA could serve as a template for making RNA, which then served as a template for making proteins. This was the central dogma of molecular biology: DNA makes RNA makes proteins. But Watson was seeing this process years before the biochemical details were worked out in laboratories. In the dream, Watson watched as sections of DNA were read by cellular machinery that created RNA copies of the genetic instructions. These RNA molecules then moved to different parts of the cell where they were used as templates for assembling proteins. It was like watching a molecular assembly line where DNA was the blueprint. RNA was the work order, and proteins were the finished products. Watson's dreams about DNA were so vivid and detailed that he later said they felt more real than his waking thoughts about the molecule. While awake, he had to struggle with abstract concepts and mathematical models. But in his dreams, he could directly observe the molecular processes that made life possible. These dream insights had practical implications for Watson's research. His visualizations of DNA replication helped him understand how genetic information was copied and transmitted. His observations of mutations helped him think about how genetic variation arose and how it could be studied experimentally. His visions of gene expression helped him conceptualize how the same genetic information could produce different outcomes in different cells. But perhaps most importantly, Watson's dreams helped him understand that DNA was not just a chemical structure, but an information storage and processing system. The molecule wasn't just biochemically interesting, it was the physical embodiment of the instructions that build and maintain living organisms. This perspective was revolutionary for its time. Most scientists in the 1950s thought of DNA primarily as a chemical compound with interesting structural properties. Watson's dream inspired insights helped establish the conceptual framework for thinking about DNA as biological information technology, a perspective that became fundamental to the development of molecular biology and genetic engineering. Watson's dreams about DNA also anticipated discoveries that wouldn't be made for decades. His visions of dynamic gene expression, where the same genetic information could be interpreted differently in different contexts, helped establish the conceptual foundation for understanding how complex organisms could develop from relatively simple genetic instructions. The dream insights about DNA repair mechanisms, processes Watson observed in his dreams where cellular machinery would fix damaged genetic information. anticipated the discovery of sophisticated DNA repair systems that weren't fully understood until the 1970s and 1980s. What's particularly fascinating about Watson's story is how his dreams seemed to bridge the gap between his biological intuition and the chemical reality of DNA. While he sometimes struggled with the molecular details during his waking hours, his dreams allowed him to experience DNA as a living, dynamic system rather than a static chemical structure. Watson's dream-inspired understanding of DNA helped establish the conceptual foundation for the entire field of molecular biology. His insights about how genetic information was stored, copied, and expressed became the organizing principles for understanding how life works at the molecular level. Modern genetic research, from sequencing entire genomes to editing genes with CRISPR technology, builds on the fundamental insights about DNA function that Watson first glimpsed in his dreams. Every genetic test, every gene therapy, every understanding of how genetic diseases work traces back to the conceptual framework that emerged from Watson's nocturnal visions of DNA in action. It makes you wonder whether DNA itself somehow communicates its secrets to the scientists studying it. Maybe molecules have their own way of revealing how they work, and dreams are just the communication channel we haven't learned to recognize yet. Maybe the next breakthrough in genetics is currently being dreamed by someone who thinks they're just having weird visions about molecular machinery. Let's close this section with Barbara McClintock, a brilliant geneticist who spent decades having dreams about corn genetics that her colleagues thought were completely crazy until they turned out to be revolutionary. Insights that earned her a Nobel Prize and fundamentally changed how we understand the dynamic nature of genes. This is the story of a woman who was so far ahead of her time that the scientific establishment essentially ignored her for 30 years, all because she trusted her dreams more than conventional wisdom. Barbara McClintock was born in 1902 in Hartford, Connecticut, and from an early age she showed an almost mystical connection to the natural world. As a child, she would spend hours sitting quietly in gardens, claiming she could feel what plants were thinking. Her family thought this was just childhood imagination, but McClintock maintained throughout her life that she could sense the inner life of organisms, particularly corn plants. By the 1940s, McClintock had established herself as one of the world's leading experts on corn genetics. She worked at Cold Spring Harbor Laboratory on Long Island, spending her days in cornfields and her nights examining corn chromosomes under microscopes. Her colleagues respected her technical skills, but they also thought she was a bit eccentric. She would talk to her corn plants, spend entire days in silent contemplation of genetic patterns, and make claims about chromosome behavior that seemed to come from nowhere. What made McClintock different from other geneticists was her approach to research. While most scientists studied genetics through carefully controlled experiments and statistical analysis, McClintock would spend months just observing corn plants, looking for patterns that others might miss. She had this almost supernatural ability to see genetic relationships that weren't obvious to more conventional researchers. In the 1940s and 50s, when genetics was still a relatively simple field, everyone knew that genes were arranged on chromosomes like beads on a string, and they stayed in fixed positions generation after generation. This was basic, uncontroversial science. Genes had specific locations on chromosomes, and those locations were stable and predictable. Any genetic map you drew would remain accurate indefinitely. But McClintock kept having dreams that contradicted this fundamental assumption. In her dreams, she would see corn genetics as a dynamic, shifting landscape where genes could relocate themselves like nomadic tribes moving across chromosomal territories. These weren't abstract dreams. They were incredibly detailed visions where she could watch individual genes, detaching from their chromosomal positions and inserting themselves in new locations. The dreams were remarkably consistent and specific. McClintock would find herself observing corn chromosomes at a molecular level, watching as certain genetic elements would literally cut themselves out of their original positions and paste themselves into new locations. She could see the molecular machinery involved in this process, enzymes that would make precise cuts in DNA, mechanisms that would move genetic elements around, systems that would repair the chromosomal damage left behind. What made these dreams particularly extraordinary was that McClintock could observe the effects of genetic transposition on corn plants. In her dreams, she would watch as jumping genes would land in different chromosomal locations and change the characteristics of the plants. A gene that controlled kernel color might jump to a new location and create entirely new patterns of pigmentation. A gene that affected plant height might relocate and produce new growth patterns. McClintock's colleagues thought this was complete nonsense. Genes didn't move around on their own. That would make genetics impossibly complicated and unpredictable. The whole field of genetics was built on the assumption that genes stayed in fixed locations, allowing researchers to create stable genetic maps and make reliable predictions about inheritance patterns. But McClintock couldn't ignore what she was seeing in her dreams and increasingly in her research. She started documenting evidence of what she called controlling elements, genes that seemed to regulate their own movement and the activity of other genes. She would spend entire seasons growing corn plants, carefully documenting chromosomal changes that suggested genes were actually mobile. The evidence was subtle and required extraordinary observational skills to detect. McClintock would notice that certain corn kernels had pigmentation patterns that couldn't be explained by conventional genetics. She would find chromosomal breaks and rearrangements that suggested genes had moved from one location to another. She would observe genetic instabilities that indicated some elements were jumping around and disrupting normal gene function. For years, McClintock tried to convince her colleagues that genes were mobile, but the genetics establishment essentially ignored her work. Her papers were rejected by major journals, her conference presentations were poorly attended, and she was increasingly marginalized as a scientist who had lost touch with biological reality. The rejection was particularly painful because McClintock's insights were based on incredibly meticulous research. She would spend years documenting the behavior of individual genetic elements, creating detailed maps of chromosomal rearrangements, and developing sophisticated techniques for detecting genetic mobility. Her work was technically brilliant, but it challenged fundamental assumptions about how genetics worked. By the 1960s, McClintock had largely stopped publishing her research on transposable elements. The scientific community had made it clear that they weren't interested in her jumping genes theory, and she focused on other aspects of corn genetics that were more acceptable to mainstream researchers. But she never stopped believing in what her dreams and research had shown her. The vindication came in the 1970s, when molecular biology techniques finally advanced enough to directly observe genetic transposition. Scientists using new DNA sequencing and cloning methods began discovering that genes could indeed move around on their own. What they found was exactly what McClintock had been describing for decades: mobile genetic elements that could cut themselves out of one chromosomal location and insert themselves in new positions. The discovery that genes could move around revolutionized our understanding of genetics. Transposable elements, jumping genes, are now known to be one of the most important mechanisms in evolution and genetic regulation. About half of the human genome consists of transposed genetic elements or sequences derived from ancient transpositions. McClintock's dreams had shown her that genetic instability wasn't a problem to be solved, but a fundamental feature of how genomes work. Jumping genes weren't genetic accidents, but sophisticated, regulatory mechanisms that allowed organisms to adapt to changing environments and evolve new capabilities. Modern genetics has discovered that transposable elements are involved in virtually every aspect of genome function. They contribute to genetic diversity, help regulate gene expression, play roles in chromosome structure, and drive evolutionary innovation. The selfish DNA that McClintock observed in her dreams is now understood to be a fundamental component of genome organization. What makes McClintock's story particularly inspiring is her willingness to trust her dreams and observations despite decades of professional isolation. She knew what she was seeing in her research and in her sleep, and she refused to let scientific orthodoxy convince her otherwise. Her persistence in following dream-inspired insights eventually led to revolutionary changes in how we understand genetics. McClintock finally received recognition for her discoveries when she won the Nobel Prize in Physiology or Medicine in 1983, at age 81. Her acceptance speech was essentially a vindication of trusting scientific intuition even when it contradicts established knowledge. She had spent her career following insights that seemed impossible, and she lived to see them become the foundation of modern genomics. The most remarkable aspect of McClintock's story is how her dreams anticipated discoveries that wouldn't be made for decades. Her visions of mobile genetic elements, sophisticated regulatory mechanisms, and dynamic genome organization predicted developments in molecular biology that required advanced technology to confirm. McClintock's research helped establish the foundation for understanding how genomes evolve, how genetic regulation works, and how organisms adapt to changing environments. Her dream-inspired insights about genetic mobility became fundamental to understanding everything from antibiotic resistance in bacteria to the genetic basis of cancer. What I find most fascinating about McClintock's story is how she maintained her conviction despite decades of rejection. Most scientists would have given up on ideas that their colleagues consistently dismissed, but McClintock trusted her dreams and observations more than peer pressure. She understood that revolutionary insights often seem impossible until they become obvious. McClintock's willingness to follow her dreams, even when they led her away from scientific orthodoxy, ultimately contributed to one of the most important discoveries in modern biology. Her story shows that sometimes the most important scientific breakthroughs come from trusting insights that seem to contradict everything we think we know about how the world works. Maybe the next great breakthrough in genetics is currently being dreamed by someone who doesn't yet have the courage to trust their nocturnal visions. Maybe the solution to understanding genome complexity is floating around in someone's unconscious right now, waiting for a dreamer brave enough to follow their insights despite what conventional wisdom says is possible. Let's close this section with Barbara McClintock, a brilliant geneticist who spent decades having dreams about corn genetics that her colleagues thought were completely crazy until they turned out to be revolutionary. Insights that earned her a Nobel Prize and fundamentally changed how we understand the dynamic nature of genes. This is the story of a woman who was so far ahead of her time that the scientific establishment essentially ignored her for 30 years, all because she trusted her dreams more than conventional wisdom. Barbara McClintock was born in 1902 in Hartford, Connecticut, and from an early age she showed an almost mystical connection to the natural world. As a child, she would spend hours sitting quietly in gardens, claiming she could feel what plants were thinking. Her family thought this was just childhood imagination, but McClintock maintained throughout her life that she could sense the inner life of organisms, particularly corn plants. What made McClintock unique wasn't just her scientific brilliance. It was her approach to research that combined rigorous observation with an almost intuitive understanding of genetic processes. While other scientists relied primarily on statistical analysis and controlled experiments, McClintock would spend months just watching corn plants grow, looking for patterns that others might miss. By the 1940s, McClintock had established herself as one of the world's leading experts on corn genetics at Cold Spring Harbor Laboratory on Long Island. She would spend her days in cornfields and her nights examining corn chromosomes under microscopes, developing an intimate familiarity with genetic patterns that bordered on the supernatural. In the 1940s and 50s, when genetics was still a relatively simple field, everyone knew that genes were arranged on chromosomes like beads on a string, and they stayed in fixed positions generation after generation. This was basic, uncontroversial science that formed the foundation of all genetic research and breeding programs. But McClintock kept having dreams that contradicted this fundamental assumption. In her dreams, she would see corn genetics as a dynamic, shifting landscape where genes could relocate themselves like nomadic tribes moving across chromosomal territories. These weren't abstract dreams. They were incredibly detailed visions where she could watch individual genes, detaching from their chromosomal positions and inserting themselves in new locations. The dreams were remarkably consistent and specific. McClintock would find herself observing corn chromosomes at a molecular level, watching as certain genetic elements would literally cut themselves out of their original positions using what looked like molecular scissors. She could see the precise mechanisms involved, enzymes that would make clean cuts in DNA, transport systems that would move genetic elements to new locations, and repair mechanisms that would heal the chromosomal damage left behind. What made these dreams particularly extraordinary was that McClintock could observe the effects of genetic transposition on corn plants in real time. In her dreams, she would watch as jumping genes would land in different chromosomal locations and immediately change the characteristics of the plants. A gene controlling kernel color might jump into a new position and create entirely new pigmentation patterns. A gene affecting plant height might relocate and produce completely different growth characteristics. McClintock's colleagues thought this was complete nonsense. Genes didn't move around on their own. That would make genetics impossibly complicated and unpredictable. The whole field of genetics was built on the assumption that genes stayed in fixed locations, allowing researchers to create stable genetic maps and make reliable predictions about inheritance patterns. But McClintock couldn't ignore what she was seeing in her dreams and increasingly in her research. She started documenting evidence of what she called controlling elements, genes that seemed to regulate their own movement and the activity of other genes. She would spend entire growing seasons carefully tracking individual corn plants, documenting chromosomal changes that suggested genes were actually mobile. The evidence was subtle and required extraordinary observational skills to detect. McClintock would notice that certain corn kernels had pigmentation patterns that couldn't be explained by conventional genetics. She would find chromosomal breaks and rearrangements that suggested genes had moved from one location to another. She would observe genetic instabilities that indicated some elements were jumping around and disrupting normal gene function. For years, McClintock tried to convince her colleagues that genes were mobile, but the genetics establishment essentially ignored her work. Her papers were rejected by major journals, her conference presentations were poorly attended, and she was increasingly marginalized as a scientist who had lost touch with biological reality. The rejection was particularly painful because McClintock's insights were based on incredibly meticulous research. She would spend years documenting the behavior of individual genetic elements, creating detailed maps of chromosomal rearrangements and developing sophisticated techniques for detecting genetic mobility. Her work was technically brilliant, but it challenged fundamental assumptions about how genetics worked. By the 1960s, McClintock had largely stopped publishing her research on transposable elements. The scientific community had made it clear that they weren't interested in her jumping genes theory, and she focused on other aspects of corn genetics that were more acceptable to mainstream researchers. The vindication came in the 1970s, when molecular biology techniques finally advanced enough to directly observe genetic transposition. Scientists using new DNA sequencing and cloning methods began discovering that genes could indeed move around on their own. What they found was exactly what McClintock had been describing for decades: mobile genetic elements that could cut themselves out of one chromosomal location and insert themselves in new positions. The discovery revolutionized genetics. Transposable elements are now known to be one of the most important mechanisms in evolution and genetic regulation. About half of the human genome consists of transposed genetic elements or sequences derived from ancient transpositions. McClintock's dreams had shown her that genetic instability wasn't a problem to be solved, but a fundamental feature of how genomes work. McClintock finally received recognition when she won the Nobel Prize in Physiology or Medicine in 1983. At age 81, her acceptance speech was essentially a vindication of trusting scientific intuition even when it contradicts established knowledge. She had spent her career following insights that seemed impossible, and she lived to see them become the foundation of modern genomics. What makes McClintock's story particularly inspiring is her willingness to trust her dreams and observations despite decades of professional isolation. She knew what she was seeing in her research and in her sleep, and she refused to let scientific orthodoxy convince her otherwise. Her persistence in following dream-inspired insights eventually led to revolutionary changes in how we understand genetics. The most remarkable aspect of McClintock's story is how her dreams anticipated discoveries that wouldn't be made for decades. Her visions of mobile genetic elements, sophisticated regulatory mechanisms, and dynamic genome organization predicted developments in molecular biology that required advanced technology to confirm. McClintock's dream inspired research helped establish the foundation for understanding how genomes evolve, how genetic regulation works, and how organisms adapt to changing environments. Now let's slow down a bit and explore the broader context of how different cultures throughout history have understood the relationship between dreams and knowledge. What we're discussing tonight, scientists receiving insights through dreams, isn't actually unusual from a historical perspective. In fact, it might be more strange that modern Western culture is so surprised by these stories. Throughout most of human history, dreams were considered a primary source of important information. Not just personal insights, but practical knowledge that could benefit entire communities. Ancient cultures developed sophisticated techniques for enhancing and interpreting dreams specifically for problem-solving purposes, creating what were essentially the world's first research and development programs based on unconscious processing. In ancient Egypt, there were special dream temples called serapeums where people would sleep specifically to receive solutions to complex problems. These weren't just religious sites, they were essentially the world's first think tanks, where priests trained in dream interpretation would help visitors understand the practical implications of their sleeping visions. The process was remarkably systematic and scientific in its approach. Egyptian physicians regularly used dream insights for medical diagnosis and treatment. They believed that dreams could reveal the spiritual and physical causes of illness. And many medical papyri include detailed instructions for interpreting disease-related dreams. The Edwin Smith Papyrus, one of the oldest medical texts in existence, describes surgical procedures that were allegedly revealed through priestly dreams, suggesting that ancient medical practice incorporated dream-derived knowledge as a standard diagnostic tool. But here's what's really interesting: the Egyptians didn't see dream-derived knowledge as fundamentally different from waking observations. They believed that consciousness could access information through multiple channels, and dreams were simply one valid method of investigation. Modern scientists having breakthrough dreams would have seemed perfectly normal to ancient Egyptian scholars, who had been using similar approaches for thousands of years. The Greeks developed even more systematic approaches to extracting practical knowledge from dreams. The practice of incubation, deliberately sleeping in sacred spaces to receive specific information, was widely used for medical, technical, and philosophical problems. These weren't random overnight stays at temples. They were carefully orchestrated programs that could last for weeks. Archimedes, the famous mathematician and inventor, regularly practiced dream incubation before working on complex problems. His discovery of the principle of fluid displacement, the eureka moment in his bath, actually came after a night spent in a temple of Asclepius, specifically seeking geometric insights through dreams. The Greeks understood that mathematical and engineering problems often required the kind of non-linear thinking that dreams could provide. Greek dream temples called Asclepians were basically ancient sleep clinics where people went specifically to receive healing or prophetic dreams. These weren't simple buildings. They were elaborate complexes with purification pools, meditation gardens, libraries containing thousands of recorded dreams, and specialized chambers designed to enhance dreaming. Patients would undergo days of preparation, including fasting, bathing in sacred springs, and studying previous prophetic dreams to understand how divine communication worked. The Greeks understood something that modern culture has largely forgotten: that the unconscious mind processes information differently than conscious reasoning, and sometimes this alternative processing produces superior results. They developed specific techniques for asking questions of their sleeping minds and interpreting the answers in practical terms, creating what was essentially a systematic approach to accessing unconscious problem-solving abilities. Chinese scholars took this even further, creating detailed manuals for what they called dream studying, using sleep states to solve academic and technical problems. The great inventor Zhang Heng claimed that his mechanical planetarium was designed entirely from blueprints he received in dreams. Chinese alchemists regularly reported receiving chemical formulas through nocturnal visions, and these dream derived recipes often produced practical results that advanced their understanding of chemistry and metallurgy. What's fascinating is that these ancient approaches to dream-based problem-solving included quality control measures. Not every dream was considered valid. There were specific criteria for evaluating which sleeping insights were worth pursuing. Dreams had to be vivid, detailed, technically coherent, and emotionally convincing to be taken seriously. This suggests that ancient cultures had developed sophisticated methods for distinguishing between meaningful dreams and random mental noise. Indigenous cultures around the world developed similar traditions, often with remarkable consistency despite having no contact with each other. Aboriginal Australians speak of the dream time as a parallel reality where all knowledge exists simultaneously, accessible through proper dreaming techniques. Native American vision quests often involve seeking practical solutions to tribal problems through induced dream states, and these solutions frequently involve technical innovations in hunting, agriculture, or medicine. The Aztecs had professional dream workers who specialized in receiving technical information through sleep. These specialists were consulted on everything from agricultural timing to architectural design. Aztec engineering achievements like Tenochtitlan's sophisticated water management systems were allegedly based partly on insights received through organized dream research, suggesting that complex engineering problems were routinely solved through unconscious processing. What all these cultures understood is that dreams provide access to pattern recognition and creative synthesis. That works differently from logical analysis. When you're trying to solve complex problems, sometimes the best approach is to feed your unconscious mind all available information, then let it process the data while you sleep. This approach often produces insights that conscious reasoning alone couldn't achieve. The scientific revolution of the 16th and 17th centuries fundamentally changed how Western culture viewed dreams as sources of knowledge. As empirical methods and mathematical reasoning became the gold standard for valid knowledge, dream-derived insights were increasingly dismissed as superstition or wishful thinking, creating a cultural shift that we're still dealing with today. This shift had profound consequences for how scientists approached problem solving. The new scientific method emphasized controlled observation, mathematical analysis, and reproducible experiments. Dreams, being subjective and unreproducible, were pushed outside the boundaries of legitimate investigation. This created an interesting paradox where many of the greatest scientific discoveries were actually made through dream insights. But scientists couldn't publicly acknowledge this without damaging their professional credibility. Francis Bacon, one of the founders of modern scientific method, explicitly warned against trusting insights that came through dreams or intuition. He argued that true knowledge must be based on careful observation of the external world, not internal mental states. This perspective became deeply embedded in Western scientific culture, creating a bias against subjective experiences that persists to this day. The irony is that while official scientific culture was rejecting dream-based insights, many individual scientists continued to rely on them privately. Galileo reported having crucial telescopic observations suggested to him through dreams, but he rarely discussed this publicly because it would have undermined his credibility with the scientific establishment. Isaac Newton claimed that some of his mathematical insights came through nocturnal visions. Though he was careful to present his discoveries as purely rational deductions, Johannes Kepler, who discovered the laws of planetary motion, wrote extensively about dreams that showed him the geometric relationships governing celestial mechanics. But he published these dream accounts separately from his scientific papers, recognizing that the official scientific community wouldn't take them seriously. This created a strange split in scientific culture, public adherence to purely rational methods, combined with private reliance on intuitive and dream-based insights. Many of the greatest scientists of the scientific revolution were essentially living double lives, using dreams and intuition in their research while publicly claiming to rely only on logic and observation. This disconnect between public methodology and private practice suggests that the rejection of dream-based insights was more cultural than scientific, a way of distinguishing modern rational thinking from primitive intuitive approaches. The consequences of this dream skepticism became apparent during the Industrial Revolution, when technological progress increasingly required creative leaps that pure logic couldn't provide. Engineers and inventors began rediscovering the value of unconscious processing, though they rarely admitted it openly. Many patents from this era were filed by inventors who privately acknowledged that their key insights had come through dreams, but publicly described their innovations as the result of systematic experimentation. By the 19th century, a new generation of scientists was quietly beginning to acknowledge the role of dreams and intuition in scientific discovery. Darwin wrote about insights that came to him in sleep, and Maxwell described mathematical revelations that occurred during dreams. But it took until the 20th century for this acknowledgement to become respectable again, as quantum mechanics and psychology began to reveal the limitations of purely rational approaches to understanding reality. Modern neuroscience has provided fascinating insights into why dreams can be so effective for problem solving, revealing that sleeping brains engage in types of information processing that are simply unavailable during waking consciousness. These discoveries are beginning to vindicate what ancient cultures knew intuitively, that dreams represent a sophisticated cognitive process that can produce genuine insights about complex problems. During REM sleep, the brain shows increased activity in areas associated with creativity, pattern recognition, and conceptual synthesis. Meanwhile, the prefrontal cortex, the region responsible for logical analysis and critical judgment, shows decreased activity. This creates ideal conditions for making novel connections between seemingly unrelated concepts, allowing the brain to explore possibilities that waking consciousness might reject as illogical or impractical. Dr. Deirdre Barrett at Harvard Medical School has conducted extensive research on problem-solving dreams, demonstrating that people can significantly increase their chances of having useful insights by focusing on specific questions before sleep and maintaining dream journals to capture nocturnal revelations. Her studies show that the sleeping brain continues working on problems that were presented during waking hours, often finding solutions that escaped conscious analysis. The key seems to be what researchers call incubation effects, when conscious work on a problem is followed by a period of unconscious processing during sleep. The sleeping brain continues working on the problem, but without the constraints of logical reasoning that might prevent creative solutions. This process allows for the kind of free form association and pattern recognition that can lead to breakthrough insights. Neuroimaging studies show that dreaming brains exhibit unusual patterns of connectivity between different regions. Areas that rarely communicate during waking consciousness begin exchanging information freely during REM sleep. This increased neural networking may explain why dreams can produce insights that seem impossible through normal thinking. The sleeping brain is literally making connections that the waking brain doesn't make. Modern research has also validated many aspects of ancient dream practices. Studies show that people who deliberately seek problem-solving dreams are significantly more likely to receive useful insights than those who don't. The practice of dream incubation, focusing on specific questions before sleep, appears to work through measurable neurological mechanisms, suggesting that ancient techniques for enhancing dream insights were based on real cognitive processes. Perhaps most remarkably, recent research suggests that dreaming consciousness may have access to subtle pattern recognition that escapes waking awareness. People sometimes solve problems in dreams using information they didn't consciously realize they possessed, indicating that the unconscious mind processes and stores vastly more data than conscious awareness can handle. This research is revolutionizing our understanding of how scientific discovery actually works. Rather than being purely rational processes, breakthrough insights often involve complex interactions between conscious analysis and unconscious synthesis. Dreams may be one of the most important but least recognized tools in the scientific toolkit, providing access to cognitive processes that could accelerate research and innovation if properly understood and utilized. The implications of this research extend far beyond understanding individual creativity. If dreams represent a sophisticated form of information processing that can solve complex problems, then developing techniques for enhancing and directing this process could have profound implications for education, research, and technological development. We may be on the verge of rediscovering and scientifically validating approaches to knowledge acquisition that ancient cultures took for granted, but that modern society has largely forgotten. As we drift toward the end of tonight's journey through the sleeping minds of scientific geniuses, let me share some lesser-known stories that didn't quite change the world but reveal just how common and strange dream-based discoveries actually are. These tales unfold like whispered secrets from the laboratory of the unconscious mind. Giuseppe Tartini, the 18th century Italian composer and violinist, created what many consider the most technically difficult piece in the violin repertoire after a dream that was equal parts musical revelation and supernatural horror story. This is a tale that bridges the worlds of art and science, showing how creative breakthrough can emerge from the most unexpected nocturnal encounters. Born in 1692 in what is now Slovenia, Tartini was already established as one of Europe's finest violinists when he had the dream that would define his legacy. But this wasn't just any dream about music, it was a visceral, terrifying encounter with what Tartini believed was the devil himself, complete with a musical performance that transcended anything humanly possible. In 1713, Tartini dreamed that he had sold his soul to the devil in exchange for unlimited musical ability. The dream felt utterly real. He could feel the weight of the supernatural contract, smell the sulfur in the air, sense the malevolent intelligence of his otherworldly patron. But then something extraordinary happened that transformed this nightmare into musical history. In the dream, the devil picked up Tartini's violin and began playing a sonata so beautiful and technically perfect that it surpassed anything Tartini had ever heard or imagined. The music wasn't just complex, it was impossibly intricate, featuring techniques that seemed to require more than two hands, harmonies that shouldn't be possible on a single instrument, and emotional depth that moved Tartini to tears even while sleeping. The devil's performance in the dream was like watching pure musical mathematics come alive. Tartini could see how every note connected to every other note in patterns of perfect mathematical beauty. The melody lines wove together like golden threads, creating harmonic structures that seemed to reveal the underlying mathematical principles of musical beauty itself. What made the dream truly extraordinary was the level of technical detail Tartini could perceive. He could see exactly how the devil's fingers moved across the strings, could hear the precise bowing techniques that created impossible tonal effects, could observe the supernatural breath control that sustained phrases beyond human capability. It was like receiving a masterclass from a musician whose abilities transcended physical limitations. When Tartini woke up, he immediately tried to recreate what he had heard, working feverishly to capture even a fragment of the devil's musical perfection. The result was the Devil's Trill Sonata, a piece so technically demanding that many violinists still consider it nearly unplayable. The final movement includes a section of trills and double stops that pushes the violin to its absolute limits, requiring techniques that most musicians spend years trying to master. But here's the really eerie part. Tartini spent the rest of his life claiming that his dream version was infinitely superior to what he managed to write down. He said that the devil's actual performance in his dream contained musical ideas so advanced that human notation couldn't capture them. The written sonata, masterful as it was, represented only a pale shadow of the supernatural music he had experienced while sleeping. This story suggests that our dreaming minds might sometimes access artistic possibilities that exceed our waking technical abilities. Tartini's unconscious somehow conceived musical structures that his conscious mind could only approximate. It's as if his sleeping brain had direct access to pure musical mathematics, allowing him to perceive harmonic relationships and technical possibilities that were beyond his conscious understanding. The Devil's Trill Sonata became one of classical music's most famous and challenging pieces, studied and performed by violinists for over 2 centuries. Yet Tartini always maintained that what he wrote was merely an echo of the true masterpiece that existed only in the realm of dreams, accessible only through supernatural intervention. There's an interesting postscript to the Kekulé benzene story that most people don't know, a second dream that came 25 years later and solved an even more complex chemical puzzle. This tale reveals how some scientists develop ongoing relationships with their unconscious minds, returning repeatedly to the same source of inspiration throughout their careers. By 1890, chemists had fully accepted that benzene was indeed a ring structure, and Kekulé's original insight had revolutionized organic chemistry. But a new puzzle had emerged that was driving researchers to distraction. Certain benzene derivatives behaved differently than the ring structure predicted, showing chemical properties that seemed to contradict everything they understood about aromatic compounds. Kekulé, now in his 60s and one of the most respected chemists in Europe, found himself once again confronting a molecular mystery that defied logical explanation. The chemical reactions didn't match what the static ring structure suggested. It was as if benzene rings had hidden properties that only revealed themselves under specific circumstances. For months, Kekulé struggled with this new puzzle, approaching it with the same methodical precision that had made him famous. But logical analysis seemed inadequate for understanding what was happening at the molecular level. The benzene ring appeared to be more complex and dynamic than anyone had imagined. Then, in a dream that eerily echoed his famous vision from decades earlier, Kekulé began seeing benzene rings that were somehow flipping, turning themselves inside out in ways that seemed geometrically impossible. In these dreams, he could observe molecular structures that existed in multiple configurations simultaneously, shifting rapidly between different forms like molecular shape, shifters. The dream showed him that benzene rings weren't static structures but dynamic systems that rapidly oscillated between different configurations. He could see the ring constantly changing its shape, creating multiple possible arrangements that all contributed to the molecule's overall behavior. It was like watching a molecular dance where the same structure could exist in several forms at once. These dreams led Kekulé to propose that benzene rings existed in what he called resonance, rapidly shifting between multiple structural forms. This insight helped explain the unusual chemical properties that had been puzzling researchers, showing that benzene's behavior reflected the average of all its possible configurations rather than any single structure. Modern quantum chemistry has proven that Kekulé's second dream was remarkably accurate. Benzene rings do indeed exist in quantum superposition states, constantly shifting between multiple configurations exactly as his sleeping brain had envisioned. His unconscious mind had somehow intuited quantum, mechanical principles that wouldn't be formally discovered for another 40 years. What makes this story particularly fascinating is how it suggests that some scientists develop ongoing relationships with their unconscious problem-solving abilities. Kekulé's dreams weren't random events, but seemed to be part of a continuing dialogue between his conscious research and his sleeping insights. It's as if the universe was using him as a reliable chemical medium, feeding him molecular revelations whenever the scientific community needed to understand the next level of atomic reality. The resonance theory that emerged from Kekulé's second dream became fundamental to understanding chemical bonding and molecular behavior. Every organic chemistry textbook now includes discussions of resonance structures, and the concept has applications throughout chemistry and physics. Once again, a German chemist's strange dream about impossible molecular geometry had revealed deep truths about the nature of matter. Alexander Fleming's discovery of penicillin is usually told as a story of accidental contamination, a mold that randomly fell into a bacterial culture and killed the surrounding bacteria. But Fleming later revealed that the accident was actually the result of following up on a series of dreams about flying spores that had been visiting him for weeks before the famous observation. Fleming was working at St. Mary's Hospital in London in 1928, studying Staphylococcus bacteria in his notoriously messy laboratory. His workspace was known for being chaotic and poorly organized, with bacterial cultures left uncovered, specimens scattered across benches, and windows frequently left open to the London air. Most scientists would have considered such conditions completely unsuitable for serious research. But for weeks before the famous penicillin observation, Fleming had been having recurring dreams about airborne microorganisms, tiny flying creatures that would drift through his laboratory like microscopic angels. In these dreams, he could see invisible air currents carrying microscopic passengers, watch spores floating through the atmosphere, observe the complex aerial ecosystem that existed in every laboratory but remained invisible to waking eyes. The dreams were remarkably detailed and scientifically accurate. Fleming could see how air currents moved through his laboratory, carrying bacteria, fungi, and other microorganisms from various sources. He could observe how these airborne travelers would settle on different surfaces, sometimes thriving and sometimes dying depending on where they landed. It was like having X-ray vision for the microbial world. What made these dreams particularly interesting was their emotional tone. Most dreams about microorganisms would probably involve germs causing disease and contamination, but Fleming's dreams featured airborne creatures that seemed benevolent rather than threatening. He would watch spores floating gracefully through the air, landing gently on bacterial cultures, sometimes creating beautiful patterns or causing interesting changes in their new environments. The dreams were so vivid that Fleming started paying unusual attention to air circulation in his laboratory. He began leaving bacterial cultures uncovered for longer periods, almost unconsciously creating conditions where airborne contamination was more likely. His colleagues probably thought he was becoming even more careless than usual, but Fleming was actually following guidance from his unconscious mind. When the famous mold spore finally landed in his Staphylococcus culture in September 1928, Fleming immediately recognized it as one of the flying microorganisms from his dreams. Instead of discarding the contaminated culture as most scientists would have done, he studied it carefully and noticed the clear zone around the mold where bacteria had been killed. The key insight that Fleming's dreams had provided wasn't just awareness of airborne microorganisms. It was the perspective that contamination might sometimes be beneficial rather than harmful. His sleeping mind had prepared him to look for healing rather than destruction, to see opportunity rather than failure when unexpected microorganisms appeared in his cultures. This dream-inspired perspective may have been crucial for recognizing penicillin's potential. Fleming saw the mold contamination not as a ruined experiment but as a possible solution to bacterial infections. His subconscious had somehow primed him to notice beneficial microorganisms rather than dismissing them as laboratory problems. The development of penicillin became one of medicine's greatest achievements, saving millions of lives during World War II and launching the age of antibiotics. It's remarkable to think that this breakthrough might have been missed entirely if Fleming hadn't been prepared by his dreams to recognize helpful microorganisms floating through his laboratory air. Fleming's story suggests that scientific serendipity isn't entirely random. Sometimes our unconscious minds prepare us to notice important discoveries by showing us what to look for. The accident that led to penicillin was actually the culmination of weeks of dream preparation that trained Fleming's awareness to recognize beneficial rather than harmful microbial interactions. As we reach the end of tonight's exploration into the secret laboratory of sleeping minds, these stories reveal something profound about the nature of scientific discovery. The boundary between conscious reasoning and unconscious insight is far more permeable than our culture typically acknowledges. Each of these tales, from Tartini's supernatural musical encounter to Fleming's beneficent flying microorganisms, suggests that breakthrough discoveries often require the kind of non-linear thinking that only emerges when rational constraints are temporarily suspended. Our sleeping minds seem to have access to pattern recognition and creative synthesis that conscious analysis simply cannot achieve. What's particularly fascinating is how these dream insights consistently anticipate developments that won't be understood for years or decades. It's as if the unconscious mind has access to a kind of knowledge that exists outside normal temporal boundaries, allowing dreamers to glimpse future understanding before the scientific community is ready to accept it. Perhaps most remarkably, these stories suggest that the universe itself might be more willing to reveal its secrets than we typically assume. When conscious effort reaches its limits, when logical analysis proves inadequate, when established methods fail to provide answers, that's when dreams seem to offer alternative pathways to understanding. The scientists whose dreams we've explored tonight weren't just fortunate recipients of random nocturnal insights. They were individuals who had learned to trust their unconscious minds, to pay attention to the strange wisdom that emerges from sleep, to follow insights that seemed impossible by conventional standards. Maybe the next great scientific breakthrough is currently being dreamed by someone who hasn't yet realized they're receiving cosmic downloads through their sleep. Maybe tomorrow's Nobel Prize winner is tonight having their first prophetic dream and dismissing it as just another weird night vision. Or maybe, just maybe, the breakthrough we've been waiting for will come to you tonight in your dreams. Well, if you're somehow still conscious at this point, which would honestly surprise me given how relaxed I'm feeling just talking about all these sleeping scientists, I hope you've enjoyed this journey through the strange intersection of dreams and discovery. It's fascinating to think that some of our most fundamental scientific knowledge came not from careful calculation or systematic observation, but from the bizarre theater of unconscious minds. Makes you wonder what revolutionary insights might be waiting in your own dreams, doesn't it? Before you drift off tonight, drop a comment and let me know where you're watching from and what time it is in your corner of the world. I always love seeing our global community of night owls and insomniacs checking in from everywhere. And if you've ever had a dream that helped you solve a problem, even something mundane like where you left your keys, I'd love to hear about it. If these stories of scientific discovery through dreams have captured your imagination, make sure you're subscribed because we'll be back next week with another exploration of history's strangest sleep experiences. Next time, we're diving into the dreams that changed the course of wars and reshaped entire civilizations. Sweet dreams, everyone. And who knows, maybe tonight you'll dream the solution to a problem that's been puzzling scientists for centuries. Just remember to keep a notebook by your bed, because the universe has a habit of delivering its best insights when we're too sleepy to remember them clearly. Sleep well, and maybe I'll see you in your dreams.